So on page 860 of your textbook here, we're going to talk about solubility rules. We've talked about solubility and what that is, sort of the measure of how well something dissolves at a certain temperature. And the solubility rules are general guidelines to help you know, at room temperature, basically, in normal conditions, what should be soluble and what shouldn't be. So you should get to know by the end of these classes here that we're studying solubility, you should have an idea when you look at a compound whether it's going to be soluble or not. You may not know exactly, but you should have an idea. There are some that you should know immediately whether this is going to be soluble in solution, like it's going to be dissolved completely into ions, or whether there's probably going to be solid in solution, like it's not going to dissolve. Okay? So the first rule, and if you look on your sheet, you should have these on your sheet. All common salts of group 1 elements and ammonium ion are soluble. Okay, so let's just unpack that a little bit. Now, don't worry about the word salts. Don't get hung up on that. A salt is basically, a compound from the first column with a halogen or with a negative ion. So a common salt. The main example would be NaCl. Okay, that's an example there. NaCl is a common salt. Group 1 elements, that's the alkali metals, the very first column. And if you look at your periodic table, it's the far left column. And also, these ones and ammonium. Ammonium is NH4+. Okay? So any of the group 1 elements, so that's lithium, sodium, potassium, rubidium, cesium, francium, and ammonium are soluble. NaCl, NH4, F. Okay, ammonium and a halogen, let's say. All right. So when you see that NaCl, is soluble. Really, anything, most compounds with lithium, potassium, rubidium, cesium, those ones, they're going to be soluble as well. Okay, that's rule number 1. Rule number 2: all common acetates and nitrates are soluble. Okay, turn to page 169 in your text real quick. So, acetates, if you look on your chart, an acetate is an ion that is CH3 COO negative. So if you have something like, let's say lithium acetate, okay, if you have this right here, lithium acetate, or if you have, anything, copper acetate, copper 1 acetate would look sort of like, this, right? Copper 1 acetate. Anything with an acetate ion, that's going to dissolve pretty readily. Okay. Nitrates, of course, nitrates. You look on your chart there, NO3 minus. So anything with a nitrate, sodium or manganese or titanium, any kind of metal that you can think of. Calcium, right? Calcium nitrate. That's going to be quite soluble. Okay. So acetates and nitrates, soluble. Number 3, all binary compounds of group 17. So binary means 2. Okay, so 2 elements of group 17. That's the halogens, except for F. F has some exceptions there. So that's not always with F. But anything else, chlorine, bromine, iodine, all right, any binary compounds with those guys are going to be soluble. Except if we have silver, mercury 1, or lead. So silver chloride, that's a halogen, but silver is one of the exceptions. Okay? So they're soluble except if they match up with one of these 3. Okay? I do not expect you to memorize these rules. No. What I said earlier was there are some compounds that you should look at and say no right away. Oh yeah, these are soluble, or these I know are insoluble. So there are a few that you should be able to recognize, but you don't have to know all these rules by memory. Don't worry about that. Okay, just stop me if you're really, really seriously confused about something, because I'm just going to kind of keep going on at a reasonable pace here. Hopefully that you're going to ingest this. Okay, sulfates, all right, if you see a sulfate, they are generally soluble, except with this list. Okay, barium, strontium, lead, calcium, silver, and mercury. Okay, so sulfates kind of 50-50, I guess, because some of these are pretty common. So sulfates are going to have to look at the chart. Oh, sulfates are SO4 2-. That's a sulfate ion. So NaSO4, Na2SO4, that's going to be what? Soluble or insoluble? All sulfates are soluble except if this is the positive ion, right? And so Na is group 1 element, so as soon as you see an Na, you're thinking soluble right away. Okay? Now, barium sulfate, BaSO4, that's this right here, and so that's insoluble, fairly insoluble. So this is probably going to form a solid. This will probably dissolve in the aqueous. Okay? Is that making some sense there? Okay. Okay, number 5, except for those in Rule 1. Now, Rule 1 is this group 1 elements. Carbonates, hydroxides, oxides, sulfides, phosphates are insoluble. Okay, so we'll list those again. You can look on page 169, okay, for those. So carbonates, going to be CO3 2-. Hydroxides, OH-. Oxides, okay, O2-. Sulfides, S2-. Phosphates, PO4 3-. So if you see any of these, okay, you're thinking, okay, probably insoluble, except if they have sodium, lithium, potassium, rubidium, those kind of things. The group 1 elements. Okay? Okay, on page 861, table A10, we have a solubility product constant chart. And this chart that I've got up here is almost identical, looks pretty close to the one that you have in your textbook there. Okay? Now, Ksp is the solubility product constant, right? And just like any equilibrium constant, it does depend on temperature. So this is room temperature, sort of lab conditions, okay? Notice that some of these numbers are really small. 10 to the negative 13, negative 16, look at this one, negative 33, right? Negative 29. So these ones are super, super insoluble because they have a really, really low product constant. You remember that from yesterday? Okay. Now the ones that have a bit of a higher constant, now what is higher? Well, I think like generally this is still pretty small, all right? But let's take a look at our solubility rules with carbonate and lithium. Is that generally soluble or insoluble? Okay, where's carbonate here? Where's carbonate? Carbonate is mentioned on which rule here? Okay, rule number 5, carbonates right here. So generally, these are insoluble except if they're matched with the alkali metals, and that lithium is in the first column. So this is fairly soluble. Now this number looks pretty small, but this is actually soluble. So I don't have it jotted down here, but I think in the past, if you match up these constants with these rules, I think we said anything above 10 to the negative, so anything greater than 10 to the negative 4, I think, is that's where the cutoff is. So greater than 10 to the negative 4 is fairly soluble, starts to become soluble, and then anything less than that is insoluble. Okay, now don't quote me on that because I don't have it written down here. I'm just trying to remember, but I think it's about 4. Now I don't see anything that's 4. So 2, I see 2, I see 5. Okay, let's check 5 because that comparing to 2 and negative 5 we could see. So what about what's PB again? Lead chloride. Okay, what about lead chloride? What do your rules say about lead chloride? Chloride is a halogen. So do you see chloride or lead? Well, here's halogens, binary compounds group 17, are soluble, except for those of silver, mercury, or, oh, here we go, lead. So generally they're soluble except if it's matched with lead, and that would be the case with this one, right? Lead chloride. So, yeah, I think 10 to the negative 4 is a good sort of cutoff because this now is fairly insoluble, the chart says. Okay, does that make sense? Okay, if you're looking at the chart, how to match that with the rules. Okay. All right, so these solubility rules help us determine whether in a solution we're going to expect a product to form or a precipitate to form. And this sort of section is called predicting precipitation. So if we mix two solutions together, sometimes we'll have a solid, sometimes we won't have a solid. And we'll be able to calculate, when that should happen and when it shouldn't. We are going to do a solubility lab, and you'll be doing some math to calculate whether you should have a product form, and we'll be actually mixing some things up in the lab, and you'll be able to see whether a product will form as well, so you'll be able to connect that. But let me explain kind of how the math works or how the logic concept works here. All right, so I'm going to introduce something I don't think I've talked about before, but experimental ion product. Okay. Now, what is the experimental ion product? Let me just explain this a little bit. You know about Ksp, right? That's the solubility product constant, and that's sort of the maximum concentration product that can happen in a saturated solution before a product will start to form, right? Sort of the maximum amount. The experimental ion product is basically the Ksp expression. Let's say it's concentration of X and concentration of 2X squared, right? Let's say it's something like that. What you would do is in the lab, you would look at the concentration of X. Let's say it equals 0.5 molar, and the concentration of something else, Y. Let's say it is also 0.5 molar. Okay, and so you have a Ksp according to this equation, right? And I should change this just so we're not too confused. Let's do X and Y here. The Ksp would be 0.5, right, times 0.5 squared. Okay. Now, if this was how you'd find the actual Ksp for a saturated solution, this is what you would do, and you'd find your Ksp. The experimental ion product basically says, in an experiment, let's say you don't have these values, but you have something else, like 0.75 and 0.2. Okay? And then you're asked whether a precipitate will form. Alright? So, let's do a little figuring with this example here. Where's my calculator? Okay, so if the Ksp, the published Ksp, and that's the kind of the wording that you'll hear, the published or accepted Ksp, and we said it was 0.5 times 0.5 squared. That was our little example. So 0.125. So the Ksp at this temperature is 0.125. So if we have a product greater than that, we're going to have what? Just ions, or we're going to have a product? I'll say that one more time. If we have a product that we determine to be greater than this, are we going to have solid in solution, or are we going to just have ions floating around? Okay, we have to go back over Ksp here. The solubility product constant is literally the multiplication of concentration of X times the concentration of Y. In this case, it's Y squared. So if this is our number, if this is the Ksp, this means that if we get an experimental ion product that's greater than this, right? Greater, that means we have lots of ions in solution, and they're going to bump into each other and form a solid. Okay? You remember the example from the other day? Like, we have 30 people can walk around in here without bumping each other, but as soon as we get more than 30, someone's going to bump into each other, and they're going to form a compound and precipitate out of our activity. Remember that? Okay? All right? So if we have a product that's greater than this number, we are going to have a precipitate in solution. We're going to have solid ending up in that solution. So let's figure it out. The experimental ion product would be the actual concentrations that we would determine in the lab. And so for X, it's 0.75. So we put 0.75 in there. And for Y, it's 0.2. All right? And then we find our experimental ion product. And this is also called the trial Ksp. Okay? So you might want to write this down. Okay? In your notes, the experimental ion product is the trial Ksp. Those are the terms that you'll hear. So 0.75 times 0.2 squared. That's going to be our experimental ion product. And what do we have here? 0.03. So is that greater or smaller than this one? Smaller. Okay, so our trial Ksp is 0.03. So do we have a precipitate forming or not? Some say yes, some say no. This number, the trial Ksp, is smaller than the given Ksp. Smaller. So no precipitate. Precipitate, again, means, yeah, a solid kind of forming out of the solution. Okay? So do you see? I don't know if I can make it any plainer here to you. But if this number that you get from your actual concentrations is smaller than the published Ksp, you do not have any solid forming. That means there's not enough ions to bump into each other to form a compound in that solution. Yes? Okay. So if the experimental ion product is greater than the Ksp, that's the published Ksp, then a precipitate should form. And what we did just now was I just kind of ran through that with you, right? This is the published Ksp, or the given Ksp. This is our trial Ksp, taken from the actual measurements, which were given here from our lab. Put them in the Ksp expression, and this is the number you get. So if it's greater, a precipitate should form. And again, think about this. It's because the solution is too crowded, right? There's so many ions in there that they can't help but to bump into each other. All right? So how do we do this? Again, here are kind of the explanation of the notes of what the example we just did. You find the concentrations of each ion. That's what we did up here, 0.75, 0.2. And you compare their product according to the Ksp expression. That's what we did. We plugged them into the Ksp expression for this, example. And then you compare that to the published or given Ksp, which is this right here. This will indicate whether you have enough ions for a solid to form. And the final thing you need to remember to try and understand this is compounds with a low Ksp, so if the published value, if you think back to this chart right here, with a low Ksp, like this one right here, they need only a small amount of ions to form a solid, right? Because the product doesn't have to be very large. So only a few ions will be enough to make a solid. But compounds with a very high Ksp need many ions to form a solid. Okay, so that's a little bit on the solubility rules how we predict whether something will precipitate will form in solution. So just take a moment to just finish jotting down these notes, and if you have any questions, let me know.